Okay, so let's do some cyclotomic polynomials. Cyclotomic fields and cyclotomic polynomials. So these are really cool. These were a very popular topic. I told you guys last semester about, or this semester, when we talked about unique factorization, about this false proof of Fermat's last theorem. And so this has to do with the mistake that that the ring of integers in these cyclotomic fields. So this means that if I take z adjoins zeta, where zeta is a root of unity, that those are not unique factorization domains. And that was the big mistake that happened in the proof of Fermat's last theorem. I sent a long email, but I will put a link in the comments about this. So you can just search Lemai's proof. Anyway, because of this, there has been a big investigation into the properties of cyclotomic fields, and there's lots. They appear everywhere. And so I am going to just say a little bit about cyclotomic polynomials now, some of the basics of cyclotomic fields. Okay, so what is a cyclotomic polynomial? So again, a cyclotomic field. Right, so Kn is Q adjoin zeta of n, where zeta of n, so this is a primitive nth root of unity. Okay, and so what is a primitive nth root of unity? So this is this here. So what are the primitive nth roots of unity? So these are generators. So zeta. So in C, cross is a primitive nth root of unity. If and only if 1, it's a root of unity, and 2, for all, let's say, zeta prime, such that zeta prime to the n is 1, we have there exists there is some j such that zeta prime to the j, zeta to the j, is equal to zeta prime. Okay, so it generates all the other roots of unity. So it's a generator for the group of nth roots of unity. Okay, so this is, in here we're viewing everything inside the complex numbers. Okay, there's another video that I'm going to do that's about what happens to these things not in the complex numbers. Okay, so these are the primitive roots of unity. So the nth cyclotomic polynomial is the following. It's phi n of x. It's this product for zeta primitive nth root. We take the product over all these x minus zetas, nth root of 1. Okay, that's what it is. And so here we could write this as the product of x minus. So so this is what the nth cyclotomic polynomial is. Okay, so this is the definition of it. All right, but there's a nice formula for it. Here's another formula. Okay, since this group here generated by these. So this is isomorphic to Cn, and the automorphism, so this is a cyclic group of order n. Cyclic order n. And the automorphism group of Cn, so this is isomorphic to Z mod NZ cross. This is by here. Let's call this, n maps to, okay, and if we use zeta as a generator for the cyclic group, we have zeta maps to zeta. Oh, okay, we can't use n. We could do m. Okay, so m is a representative of here, of this is Z mod NZ cross. Okay, this is the map it goes to, and this thing is an automorphism of, well, I've written it as this thing, and so this is the automorphism group, and this is something we talked about in the group theory class. Okay, that how many generators are there for a cyclic group of order n? Well, there are phi n of them. So this proves. So this okay. So this is what we have, and this shows that the number of primitive nth roots. So this is equal to the number of generators of Cn, and this is equal to phi n, and this is equal to the cardinality of Z mod NZ cross, so the units in this thing. Okay, so in particular, this polynomial here, this has degree of here, this is the Euler phi function. Euler phi. And just as a reminder, how does Euler phi work? So on two primes, p to the a, q to the b, this is phi of p to the a, so q to the b. That follows from the fact that this thing can be, broken up into pieces, and broken up into pieces according to their elementary divisors, right? And for these prime powers, so this is p minus 1, p to the a minus 1. Okay, so that's how that's how you can compute the degrees of these things. And all right, so this polynomial is irreducible. So one of the exercises that we did from Eisenstein, so an exercise from Eisenstein, from the Eisenstein chapter, so is that that phi n is irreducible. So it's irreducible as a polynomial in the integers, and hence irreducible as a polynomial over q adjoint x. Okay, and so this is the minimal. So phi n of x is the minimal polynomial of a primitive nth root of unity. So let me just say that in words, is that these cyclotomic polynomials, so this is the minimal polynomial of primitive nth roots of unity. All right, so that in turn gives us a formula for the degree. So since Kn is isomorphic to, well, Q adjoin zeta n, one of these things, and this is isomorphic to Q adjoin x modulo this minimal polynomial, right? This tells us that the degree here of this extension is Euler phi of n. Okay? All right. All right. So let's kind of just do some computations. So how do let's try and get a hang of what these cyclotomic polynomials do, or how to work with them, and how they come from x to the n minus 1. All right. So this is really, maybe this is the most important part of the whole thing, right? So working how to work with these things. So let me go back. Okay. So all right. So let's look at let's look at just kind of, let's look at the polynomials x to the n minus 1. Okay. So these are the things which have all the roots of unity, not just the primitive ones. Okay. So for n is equal to 1. Okay. We have the polynomial x minus 1, which has 1 as a root, right? And so by definition, we define phi1 of x to be x minus 1. All right. For n is equal to 2, similarly, we have x plus 1, right? So I mean, this is x squared minus 1, right? And then and so this factors into two pieces. And so phi2 is the new piece. So it's x plus 1, which gives you minus 1 as the new root. For n is equal to 3, we have this. And this thing factors as x minus 1. And then we have 1 plus x squared. So that's this formula. This piece is old, right? And the new piece, so this is phi1 of x and phi3 of x. So this is this piece here is the new piece. And so this has roots of unity 2 pi I divided by 3, and its conjugate, its complex conjugate, and that is 4 pi I divided by 3. And maybe I can draw this one. So we have this, and then we have the two complex conjugate roots. This is on the unit circle in the complex plane. All right, so let's go back. N is equal to 4. What happens at n is equal to 4? So x to the 4th minus 1. This is a difference of squares. This piece breaks into the previous pieces. So this is phi1 of x, phi2 of x, phi4 of x. Okay, and this thing, so the primitive roots of unity here are, so zeta here is just I, which is the square root of minus 1, and or minus I, right? That number, if we were going to draw it in the complex plane, is here. So this angle is 2 pi divided by 4, which is pi over 2, which is this 90-degree angle here. Minus I is here, right? So we have I and minus I. Okay, and then these are the third roots of unity. All right. Okay, so that's the fourth one. Let's do the fifth one. This is another prime number. So we have x to the 5th minus 1, and we just have x minus 1, 1 plus x squared plus x cubed plus x to the 4th. And we have the same thing that we had previously. So this is this is the same thing for n is equal to 3. X squared plus x cubed plus x to the 4th, right? And I guess we could do n is equal to 6, right? So for n is equal to 6, x to the 6th minus 1, this is x cubed plus 1. So this is, here we go, x minus 1. And then we have 1 plus x squared. And I think we have x plus 1. So here you can notice that minus 1 is a root of this since it's odd. And then we have 1 minus x plus x squared. All right. So let me just kind of write how this works out. So this is phi 1 of x. This is phi 2 of x. This is phi 3 of x. And this thing here is phi 6 of x. All right. So here are the roots. So phi 6 of x. Phi 6 of x is degree 2. It's 1 minus x plus x squared. Let's just check this formula again. That we said that that this was the degree of this was the Euler phi function, right? So phi of 6. So this has two factors, 2 and 3. So this is 2 minus 1 and 3 minus 1. And so that is 1 times 2, which is 2. Okay? So it's a degree 2 polynomial, and there's only 2 of them. Okay. And so this just kind of goes on in general, and so the kind of the general thing that happens, and which I'll leave it to you guys to look at up in the book, is that x to the n minus 1. So this will be a product over the things that divide n of phi d of x. And so note that this is a formula that we have for this. And so if you can compute these inductively using this formula. Note that these divisors here, so the divisors include d is equal to 1 and d is equal to n. All right. All right, and so okay, so like one thing that you can check, so maybe a good exercise to do is, check that, okay, check this and check that n is equal to, say, the sum of d divides n of phi of n. Right. So this is something that you could try and do if you don't believe me. All right. So that's all I want to say about cyclotomic polynomials and cyclotomic fields for now.